Hello, CHEM 120 students. So this is Professor May Joan Aguila. And for this video lecture, we're going to look into some introductory discussion about a special topic. And this is on organometallic chemistry. So organometallic compounds, these are some of the known catalysts in many industrial processes. In fact, they are quite known that those scientists who discovered these catalysts have been awarded the Nobel Prize in Chemistry. So there are several of them. And some of those are actually shown on the screen. So you might have heard the name Sigler and Natta, and Fisher and Wilkinson. And in the recent times, 2000 and above, we have Knowles, Nuyori, and Sharpless for their asymmetric reactions. And Jovan, Grubbs, and Schrock. Actually, Grubbs and Schrock are the one who prepared the catalyst for metathesis reaction. And then we have Heck and Negishi and Suzuki for palladium catalyzed cross-grouping reactions. So for these examples, the organometallic compound that they use is for application as catalyst for the reactions mentioned. Organometallic compounds are actually metal-carbon bond. So if it has a metal and a carbon bond, it is strictly an organometallic compound. But in recent times, this has been changed a little bit and expanded to include some complexes wherein the ligand behaves similarly as a carbon-based ligand, and hence the reactivity of these complexes are very similar to that of the metal-carbon bond. Sample of which would be hydrogen in the hydride form. And sometimes, so as not to be confused about the term organometallic, several chemists actually propose the use of the term metal organic compounds. So somewhat to encompass all the other types of ligands possible that behave in a similar way as a metal-carbon bond. So organometallic compounds, if you're going to look into the metal, the metal can be coming from a main group. So maybe you've learned or you've seen some examples of this even in your organic chemistry. So one example is shown on the screen. So this is the sodium as the metal. And then you have over here the ligand. We use the pen. So you have over here the ligand. This is the carbon-based ligand, which is the cyclopentadienyl ligand. And then this one is dimethoxyethane. So 1,2-dimethoxyethane as another ligand. So this is sodium. Another example of this, although not shown, is the Grignard reagent. So I think you're more familiar with that. And of course, metals can also be based on transition metal. So we have an example here, ruthenium, and this is ethylene. So the ethylene is the carbon-based ligand, and then we have a phosphine-based ligand over here. And here we have molybdenum. So this is the ChemDraw illustration, but this is the crystal structure. So molybdenum with 3 different types of carbon-based ligand. One is referred to as allyl, and the bonding with the metal is in the 8-3 form. So this is not that foreign to you anymore because this is part of what we've discussed or what you've had in the module for coordination chemistry. So we also have this butadiene, and it is in the 8-4 type of bonding mode. And we also have the cyclopentadienyl, the similar cyclopentadienyl as with sodium over here. And here, it is in the eta 5 bonding. So I actually have training as an organometallic chemist, and I have some experience in both, a little bit for main group, but I just basically use it to start off some reactions. Maybe you've heard about N-butyl lithium, and N-butyl lithium is a powerful reagent to introduce a carbon anion. So the butyl group there is actually in the negative charge form. And then I use that to further do some reactions, but my main focus is actually on copper. So that's a transition metal-based type of organometallic compound. So for organometallic compounds, one of the things that we typically use to characterize an organometallic compound is to consider its electronic configuration. And Sidwick actually mentioned that the metal in an organometallic compound will take up the same valence count as the noble gas that terminates when you consider the period where the metal belongs. So this is sometimes referred to as the 18 electron rule or the effective atomic number. Okay, so 18 electrons. So where does the 18 electron come from? So if you consider the metal, and it should be behaving with the same valence count as the noble gas that terminates in the period. So that would mean it should have the s orbital field plus all the p orbitals field, and then all the d orbitals field. So 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals with 2 electrons each. That's why it is 18. So it is said that if we have a chemical species, an organometallic chemical species that has an electron count of less than or greater than 18, that is more susceptible or more reactive as compared to if it has 18. So the stable electronic configuration assumes 18 electrons. Sometimes though, because of the nature of the structure, for square planar, they are more commonly found as 16 electron. So square planar compounds usually have 16 electrons total count, okay? But that means that it can still accommodate 2 more electrons, but there will be some changes in the geometry if it accommodates 2 more electrons. So we have here a summary of those central metals under the transition metal, which can usually have fewer than electrons, or 16 or even 18 electrons. It can have 16, particularly if it's in the square planar, but usually those that are in the middle are 18 electrons. So how do we do electron counting? There are 2 general methods of doing this. So we have what is known as the covalent method or the neutral ligand method, and the donor pair method or the ionic method. So for the neutral method, you're going to consider the metal electrons, including both s and the d electrons, because that's the valence electrons for the metal in the neutral form. So this should be metal 0. For the ionic method, the metal is already in its charged form. So most likely it's in the it is in its cationic form. So consider the oxidation number. So that's the amount of electrons that is lost. And usually the s electrons are lost. So most likely you're going to calculate or determine the Dn count, or the Dn electronic configuration for the metal. And then in terms of the differences in the ligand, for the neutral ligand method, you're going to categorize two types of ligand. So those that can donate 2 electrons, and usually these are neutral 2 electron donors, and those that can donate 1 electron, and these are 1 electron radical donor. So the neutral is considered to, well, the ligand X type, which is a 1 electron radical donor, it is considered to make a covalent bond with the metal in the truest sense of covalent bond that we know. So 1 electron will be coming from the metal and another electron will be coming from the ligand. But this one, the L-type ligand, so both electrons are actually coming from the ligand. So this is a coordinate covalent. Or what is known as the dative. So dative bond. So dative bond. So for the donor pair method or the ionic method, regardless if it is neutral or charged, the electron would be, or the ligand would be considered as a 2 electron donor. Okay. And then some considerations, if the species is positively charged, so you need to subtract by the number of the amount of electrons that you need to subtract from the count would be the magnitude of the charge. If it is negative, you need to add up by the magnitude of the charge. So I think in the donor pair method is a little bit easier to figure out because the ligand, either with is neutral or charged, these are all, excuse me, considered to be a 2 electron donor. For the neutral formalism, we need to be a little bit more familiar with this L-type or X-type of ligand. So these are some examples of the 1 electron donor or the X-type. So if you notice, these are the ones that are actually, if you consider this in the ionic method, this will be the charge. So these will be the ones that will bear negative charges. So we have H dot there. So in the ionic method, the counterpart is hydride. And then we have this usual 2 electron donor, which are the neutral molecules such as carbon monoxide, the phosphine base, and so on. Okay. And we also have some differentiation in terms of the type of adduct that is formed by these 2 electron donor. So usually, so this would be for the usual 2 electron donors such as carbon monoxide, you have a clear lone pair that is being donated to the metal. Here, this happens as well. So this is a 2 electron donor, but in this case, the double bond or electrons in the double bond will be donated to the metal. So that's why this becomes a pi adduct. And in this case, electrons from the single bond, which is a sigma type of bond. So it will be donated to the metal. So that's why this is a sigma adduct. In terms of strength, clearly the lone pair donation is the strongest, and the sigma donation will be the weakest, because if you donate this, this will essentially break the bond or will cause the bond between HA to weaken. So some more examples of ligands. Now, there are instances wherein it is not a clear L-type or X-type. Usually, it will be a combination such as this one. So this is an LX type. So they are 3 electron donors. We have the allele over here. So this is allele, the one that we've seen before, the eta 3 allele. And then we have for 4 electron donor. So it can be an L2 or an LX2. So we have the butadiene over here. And this is a cyclooctadiene over here at the side over here. And some more of the higher order electron count, we have the cyclopentadienyl and its derivative. So this is the eta 5 cyclopentadienyl. So C, it is an L2X type. So 2 would be, actually, if you draw this in such a way, it is not in this resonance form. So this would be something like this. So 2 double bonds, and there's actually a lone pair here, but this is charged. So that's why this is considered to be the X-type ligand. And then we have greater than 5 electron donors, such as the benzene, when benzene is used, or the arene ring is used. So this is an eta 6 type of coordination. Okay, so just to compare, this is for the neutral ligand method. And we have here the typical ligands that we see and what their designation is. Are they L or X or even the combination? So we don't have much problem with this neutral ligand, but for ligands such as, say, the hydride over here, so the hydride, so this is H dot, so it is an X type of ligand. So 1 electron to be donated. In the ionic or the donor pair method, so this is hydride, as we know, so H minus, and you can see regardless if it is neutral or ionic, so we have 2 electrons being donated. Okay, with that, I think we'll have some examples of how to figure out the electron count. So we have here palladium, and palladium actually is coordinated with this. This is a PCP, pincher type of ligand. So for this case, we can actually use both the neutral and the neutral formalism and the ionic formalism. So for the neutral formalism, palladium, since we're considering both the S and the D electrons, it will have 10 electrons. So you should be able to check it out from the periodic table. Okay, so this is 10 electrons. And then the phosphorus over here, they are actually connected to the palladium through the 2 lone pairs. So the 2 phosphorus is a dative, so each would be donating 2. And then we have here hydrogen. The hydrogen actually, when you break this, it will become H dot, and one of the electron will come from palladium. So the hydrogen is an X type, so 1. And then here is actually carbon, and carbon also is an X type. So carbon 1. So if you total this up, this is 16 electrons. For ionic, you should be able to figure out the charge first. Hydride is -1. The phosphorus site actually here is 0, but carbon here is -1. So palladium is 2+. So palladium 2+, so it removes 2 of the electrons. You're left with 8 electrons. So this is a D8 metal. But in all cases, all those ligands, you have 4 ligands. So the 2, phosphorus 2, hydride 2, carbon of this iron ring would be 2. And we have 6 electrons as well. Okay, so what is important in the neutral is you should be able to know if it is L or X type. On the other hand, for the ionic method, you should know the charge of the metal. Now, for this case, this is the one wherein you have a metal-metal bond, and it is actually a symmetric one, and it is a little bit easier to figure out. So what you can do is just figure out half of it, since this is symmetric, and we can consider this side to be the same as this side. But for me, it will be a little bit harder to figure out the charge, the oxidation state of manganese here. So I think it is easier to use the neutral method. So for manganese is actually 7. It has 7 electrons. So 5 from D and 2 from the S. And then the CO, you have 5 CO over here. Each CO is a dative bond type of ligand. So it's an L type. So sorry, this should be 5, which results to 10. And then a metal-metal bond, if it has a single bond over that, each one is considered to be donating 1 electron. So from the metal, manganese bond, you have 1 electron. So the total of this is 10 plus 8, so 18 electrons. And our assumption is this is symmetric, both sides are actually 18 electrons. All right, so again, for me, it's a little bit easier to figure out this using the neutral method or the neutral formalism, because it is tricky to assign the oxidation state for the metal in this structure. So for organometallic compounds, although we're not really going deeper into this, we're going to just highlight some important considerations. One of which is what is known as the pi back bonding. So when the ligand coordinates with the metal, for example, we have here carbon monoxide. So the carbonyl ligand, with it coordinates to the metal to form the sigma bond. So what happened is the lone pair is being donated to the empty acceptor orbital of the metal. Now, because there are orbitals in the metal, particularly the d orbitals in the metal, that is of the same symmetry as the molecular orbital of CO, particularly the empty pi star orbital of CO. So what happened is there is a transfer of electrons from the metal to the ligand. And this is referred to as the pi acceptance or the pi back bonding. Back bonding because the direction of electron flow is from metal to ligand. So this is just showing us one of the d orbitals that is compatible, or we can see this is a view that is parallel to the screen, and this is perpendicular to the screen, just to see what is this pi acceptance or pi back bonding. So for ligands wherein you have the possibility of this pi back donation. So this can be considered as an additional interaction between the metal and the ligand. So overall interactions considering both the sigma donation and the pi back bonding. And actually for carbon monoxide, which can also function as a bridging ligand, this is how it looks like as a bridging ligand, wherein you have the sigma donation to both the metals and still pi type of donation from metal to ligand in this illustration. So actually the extent of pi back bonding in organometallic complexes is sometimes their spectroscopic signals that they use to characterize the metal. So they will try to follow the changes in the frequency of carbon monoxide in the IR spectrum. And what we know is because of this pi back bonding from metal to ligand, from metal to the carbon monoxide, and the nature of the molecular orbital that accepts the electrons from the metal, these are pi star, so antibonding. So if you increase electron density in the antibonding type of molecular orbital, you're basically weakening the bond in the molecule, so the bond between carbon and oxygen. So there's lengthening in the CO bond, so that means the wave number for the CO will shift a little bit lower, or there will be lowering in the wave number associated for carbon monoxide if there's significant pi back bonding in the complex. Another type of interaction, which is particular for dihydrogen, H2, and this is the formation of the sigma complex. So the group of Kubas, they are the ones who first isolate this molecular hydrogen complexes. This is quite similar to what I've shown you in the previous slide, but in this case, we have dihydrogen. So this is using tungsten as the metal. And then you see over here, this is the dihydrogen. So what is interesting about this is the coordination is via a sigma type of sigma donation, wherein the sigma, so the sigma MO is involved. So electrons from the sigma molecular orbital, so it is filled for hydrogen, it will be donated to the orbital of the metal for the sigma donation. So, and it is also capable of experiencing this pi acceptance similar to the pi back bonding, but not that high extent, okay? Because in this case, we have, this will now be the sigma star antibonding instead of a pi star antibonding. Maybe you'll be asking, how come it's pi acceptance? Because of the nature of the interaction of the metal orbital and the sigma star. Although it is a sigma star, but because the interaction is sideways, so you can see it quite clearly in this diagram. So the interaction is sideways, it is still a pi acceptance type of molecule. So for sigma bonds or sigma bond type of complexes such as for dihydrogen, this is the important interactions that can be seen in the molecule. So now we're going to shift a little bit and try to look into some of the common reactions of organometallic compounds. So the first one is actually very similar to what we had for the coordination complexes or the Werner type of compounds. So ligand substitution. So in this case, basically, if you're going to consider the valence count, it will not increase above 18 before and after. So reactant side and the product side. So this is an illustration of what a ligand substitution is. So with either ligand X or another carbon monoxide. So from the dissociation of carbon monoxide, and then you add up another carbon monoxide. So ligand substitution. So the next ones are actually what unique for organometallic compound, and this is the oxidative addition and reductive elimination. So they are sometimes taken together because they are the reverse of one another. So you can see in this diagram or in this reaction, so the going to the right would be your oxidative addition wherein XY is added into the metal. And when you remove XY, that would be reductive elimination. So by the term, so the addition of XY results to the metal being more oxidized, and the removal of XY from the coordination of the metal when you go from right to left, that is actually reductive in process at the point of view of the metal. And these are some changes that occurs if you consider the coordination number from the metal points of view, for oxidation state of the metal, and the electron count. For oxidative addition, all of this increases by 2. By reductive elimination, all of this decreases by 2. These are some examples. So from a 16 electron, and then you have a coordinated H2. We have the 18 electron 5 coordinate complex as shown. So this is actually a sigma bond of complex. And then when you break the hydrogen together, that part actually is the oxidative addition. This is really the oxidative addition step. So you can see this is broken and the hydrogens are added. So it becomes a 6 coordinate from a 4 coordinate, and then you have 18 electron to 16 electron, and you increase the rhodium charge from 3 to 1. And then this is another example of oxidative addition, but in terms of mechanism, there are actually 2 possible mechanisms wherein first off, somewhat stepwise process, the metal is added first, but then in the second step, the iodide is added first. But if you take a look into the initial complex and the final complex, that it's still about change in coordination by 2, oxidation state by 2, and electron count by 2. This is an example of a reductive elimination wherein you basically remove one of these metal groups and the hydrogen, okay? And then you generate the methane, and this is a 16 electron platinum 2 complex. The next type of reaction is referred to generally as insertion. So by the term, so you have a molecular fragment that gets inserted in between the ML bond. So somewhat the ML bond gets broken, but the L does not leave technically from the coordination sphere, but it is connected to the molecular fragment. So we have what is known as the 1-1 insertion. So this is an example of which. So you can see in here, actually the bond that is broken would be this MX bond, okay? And this CO bond is inserted in between this MX bond. Okay, so this is a 1-1 insertion. So these are some example of which, so it might be a little bit tricky to figure it out, but this is a labeled CO. And you can see over here that actually this can be either this one of this CO gets inserted in between the metal bond, and the resulting vacancy in the coordination is filled up by this labeled carbon monoxide. And then we have what is known as 1,2 insertion and beta hydride elimination. I combine these two in the presentation because similar to OA and RE, they are the reverse of one another. So we have here, this is the 1,2 insertion. So 1,2 insertion. So what happened is, again, this bond is being broken, and this coordinated alkene gets into or in between this MX bond. But it is a 1,2 position because if you consider this as position 1 and position 2, this X is transferred to position 2. Okay. It's not quite clear in here because you can see that, well, this position 1 is the one that's coordinated to the metal. So here is an example, and this is actually one of the process that is involved for the lengthening of the or polymerization using alkene. So you have here your 1,2 insertion, and then you're creating a vacancy over here that is previously occupied by this hydride. So you can coordinate the ethylene there and then do another 1,2 insertion, and you're basically lengthening it. Now you have a 4-carbon group. And this is a beta hydride elimination. So starting off from here, so you have 1,2 insertion, so you have over here. But when you do the beta hydride elimination, this follows in the same way as you're forming alkenes, the Side-Ceph rule. So you're basically going to form the more stable alkene, which is the more substituted one. So this is a beta hydride elimination. So technically, this hydride is the one that is broken. So you'll be generating a double bond over there. So those are the typical reactions that we have. So, well, ligand substitution, oxidative addition, reductive elimination, insertion 1,1,1,2, and beta hydride elimination. Now, I'm just going to show you some example of, well, not some, one example of how essentially these factors in, and this is the alkene hydrogenation by the Wilkinson's catalyst. This is the Wilkinson's catalyst. It is rhodium with phosphorus or phosphine and chloride. You can see there's really no, the catalyst itself, there's really no metal carbon bond. This is the one that can be synthesized nicely in the lab. It can be bought. So, well, now I think it is more appropriate to be referred to as a pre-catalyst or precursor catalyst rather than really the catalytic species for the reaction. So some observations that they found, the reaction is highly sensitive to the nature of the phosphine. So if you change those phosphine groups, highly sensitive to alkene, small extent of dissociation of triphenylphosphine from the Wilkinson's catalyst in benzene. And when you have the Wilkinson's catalyst in the presence of atmospheric hydrogen, you'll generate this species, which is the this one. So basically, it added up into the metal. All right, taking that in consideration, actually they are able to, they did a lot of reactions and experiment on this, and they are able to generate a mechanism showing how this works. And that one is presented in the next two slides over here. So just basically going this a little bit. So we have the first step would be an oxidative addition wherein hydrogen is added into the rhodium center. And then maybe you have a ligand substitution because usually you need to empty out or have a vacancy because rhodium is already saturated in this sense. So you need to have a vacancy so that another ligand can come in. And that another ligand would be the olefin or the alkene. So as you can see in this structure over here. And then afterwards, you'll be having this, you have an alkene, you have hydrogen. So you'll be having this 1,2 insertion. And they found out in their experiment that this is the rate determining step. And then eventually, when you have this series of lengthening maybe, and then you can have reductive elimination wherein this can be cleaved. So this can cleave and combine together and basically say you're forming an ethane. So this is in a reductive elimination fashion. So now you generate the product that you want. So the hydrogenated alkene, and you're generating back the one of the catalytic species essentially in the reaction. Okay, so that's it for our introduction of organometallic chemistry. I hope you got interested about this. If you're really interested, I'll let you know more a little bit about this as part of my research topics. All right, see you later, guys.